A ketone or an aldehyde can be combined with a secondary amine in the presence of an acid to form a molecule called an enamine. This is a molecule that has the alkene functional group as well as the amine functional group. So that's where it gets its name. The reagent or the reactant that we're using for this is a secondary amine. A secondary amine is a nitrogen that has one hydrogen and two R groups. I'm going to go through the mechanism of the synthesis of the enamine, and then we're also going to look at a retrosynthesis, converting the enamine back to an aldehyde or a ketone. This reaction is going to start by the acid catalyst protonating the oxygen of the carbon-oxygen double bond. That's going to give us an oxygen with a positive formal charge and that extra hydrogen on there. And then once that has been formed, the amine, lone pair of electrons on the nitrogen will attack the carbonyl carbon and cause the carbon-oxygen double bond to be converted to a single bond. This is going to create a bond between the carbonyl carbon and the nitrogen of the amine. There's going to be 4 bonds on this nitrogen, so it's going to have a positive formal charge. And then we'll have this OH group up top. The conjugate base of our acid catalyst, which is HSO4 minus, is going to be used to grab that proton off of the nitrogen and remove it, put a lone pair of electrons onto that nitrogen, so the nitrogen no longer has the positive formal charge. That's going to give us this molecule right here with a lone pair on the nitrogen. And since I'm drawing lone pairs, I might as well draw all of them. So after this step, the acid, which has been reformed, so we've reformed the sulfuric acid, it's going to protonate the oxygen again. Almost draw my arrow in the wrong direction. And that will give us this molecule right here. We have a second hydrogen on the oxygen, and we've got that positive formal charge on the oxygen has come back again. And there's this molecule. Now in our next step, the lone pair of electrons on the nitrogen are going to come in and form a carbon-nitrogen double bond. The carbon-oxygen bond will break. This will get rid of the OH2 as a water molecule, and that's going to form this, which kind of looks like an imine. That's not a carbon, that's a nitrogen. We looked at imines in the last video, and we've got positive charge on that nitrogen again. The imine, the next step that's going to happen, this is not going to stay as an imine because we can't remove anything from this nitrogen to get rid of the positive formal charge. So the next thing that's going to happen is a little bit of kind of rearrangement, shuffling of things in this molecule. The conjugate base of the acid, HSO4 in this case, is going to grab a hydrogen from the carbon that is part of the carbon-nitrogen double bond. So it's not going to pick this guy right here. It's looking for a hydrogen that is on the carbon that is attached to the carbon-nitrogen double bond. It's going to grab one of those hydrogens. It is going to move those carbon-hydrogen electrons in to make the carbon-carbon double bond, and then put the electrons from the carbon-nitrogen double bond back onto the nitrogen atom. So that is going to give us, I know that I've got some really weird bond angles here, but I'm trying to just kind of keep all the atoms in the same place to make it a little bit easier for your eyeballs to see what's going on. That's going to give us this product, which is the enamine. Let's draw it a little bit prettier, make it look a little bit nicer. There it is. And I've just kind of turned it around and fixed the bond angles a little bit. So this is our enamine product. Now, in terms of retrosynthesis, so if we were starting with an enamine and being asked to convert it back to an aldehyde or a ketone, this would be done using water and some sort of acid. I've just written H3O+. If we needed to do this, we could just backtrack our way through the mechanism all the way back to the beginning. That's a little bit tedious to do. So if I'm being asked to reverse the enamine synthesis or do a retrosynthesis, then what I do is like to kind of go through a series of tricks or little steps along the way. Now notice this particular enamine that I'm using is exactly the same as the one that we just synthesized. So we already know that these are the products that we need to be making. And it's kind of helpful to have that in mind as we go through this. So the first thing that I like to do when I'm doing this, and this is not the mechanism, I want to make that clear. I like to recognize that the carbon-carbon double bond of the product used to be a carbon-nitrogen double bond. So what I'm going to do, I'm just going to kind of draw these little dotted arrows. I'm going to move that double bond so that it's up between the carbon and the nitrogen. And I'm not changing any of the R groups that are on the nitrogen or anything. I'm just repositioning the carbon-carbon double bond, making it a carbon-nitrogen double bond. The enamine as well as the imine, they are formed at this particular site, at the double bond site. So this is where we need to break the molecule apart, and we're going to break it into two pieces. Literally, I'm just going to kind of separate it into two pieces. So we've got this, let me make a little dotted line here so we can show this is our next step. Dot, 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 dot. These are our next steps. So I'm going to break the molecule. I'm going to draw it as two parts. There's going to be this half of the molecule, and I'm going to put a box here because we need to figure out what goes at the end of this double bond. And then we also have this CH3 and CH3. We've also got something hanging out here on the end of this as well. And this nitrogen, this is not going to be a double bond. I mean, I could draw it that way originally, and we can see why it's not going to be a double bond. So we've just got to figure out what's going to go into these parts. We're using water to break this apart, so that means that we want to be putting water molecule, the components of a water molecule into these boxes. We do know that one of the products of this is going to be an aldehyde or a ketone, so we need to have a carbon-oxygen double bond. So there's the aldehyde or ketone, because again, we have to make a carbon-oxygen double bond. So there's that. So the other part that we're putting on here is hydrogen atoms. And look at that. Now that doesn't make sense because we don't like to have two bonds to a hydrogen. That's just not favorable. So one of those bonds is actually not going to be there. It's going to be the lone pair on the nitrogen. You might be wondering, where did that other hydrogen go? Like, we're adding water molecule, so we added one oxygen here, we added one hydrogen here. What about the second hydrogen? Where did it end up? Well, when we, on paper, when I took this double bond and I moved it over into this place, this carbon atom had two hydrogens on it, and when I moved that double bond, I had to put hydrogen atom, an extra hydrogen atom on this carbon. So in terms of where all the hydrogens ended up, one of them went right here. So one went right here, the other went right here, and then the oxygen of the water ended up in this spot. These two that I've just drawn here, these are the products of this reaction. Or if you were being asked to show how to synthesize this enamine, this would be the aldehyde and the amine that you would need for the synthesis.